joining me once again this lovely Monday. As we have been doing over the past few weeks, we will be looking at an article from This Week in Neo4j. So This Week in Neo4j is our weekly newsletter. It's something that is put together by my colleague Mark Needham, and it's a really great overview to give you a flavour of what's been going on in the graph world. So it's usually about a 2-3 minute read each week, and it just gives you the highlights of each of the articles, and then you can pick something that may be of interest to you and explore further. So if you're not already subscribed, I recommend that you do, and I'll get the link for how you can subscribe to that in the chat during this session. But this week, what I'm going to be having a look at is the two articles. So you get a bonus article this week. The two articles which Jasper Blues has been putting together, called Rock and Roll Traffic Routing, and this is part of his blog series he's doing on Saxoburg. So I will put the links to those articles now in the chat. So for those of you who want to read those and follow along, I've put those in just now. And what I was going to say as well is I am going to be doing these in Sandbox, so I'm just going to quickly give you Jasper's Twitter handle as well, so if you want to follow him on Twitter to see when he does his next blog post, you can do that as well. And I am going to be using Sandbox today to go through his articles. So the nice thing about the Neo4j Sandbox is that you don't have to download anything, you don't have to install anything. You can just basically get up and running quickly. So specifically, I'm going to be using the Graph Data Science Sandbox. So I'm going to be using the Graph Data Science Sandbox. So I'll show you, I'll spin one up, so we'll do that together. You can see where I click. So Alex has just put the link in for the Sandbox, but specifically we're using the Graph Data Science one for those of you who are being organised and getting one set up beforehand. If you've got any questions during the session, please put them in. So I've noticed there's a couple of questions coming in. They're not related to the article, so if we've got some time, I'll pick up on those at the end of the session. One's questions that are related to what we're looking at today. I'll try and answer those sort of in situ. So anything that's not strictly related, I will see if I can answer those at the end of the session. Okay, so let's get going. So Jasper Blues has posted a couple of articles. So one was put in I think about 2 weeks ago, and there was another one that came in last week. And what Jasper's looking to do is he's looking to show and teach you how to use the graph, and he's doing it on this story he's putting together. So it's a story about the Saxoburg series. So you can have a look at that, and this is what we're looking at. So this will be the first link that I put in that we're going to be looking at now. And effectively what Jasper starts to talk about is, you know, how do these various online maps that you have, you know, how do they work? So how are they able to offer this quick routing to be able to understand what's going on? And what he does in these two articles, so the first article, he starts to show you the idea of the graph and how things are connected, and how you can start to bring back different paths about how two different points are connected. And then in his second article, he starts to show you how you can use graph algorithms to solve that problem. So using graph algorithms to efficiently solve these routing questions. So he introduces this town called Saxoburg. So we've got a map here, and as you can see on the map, we've got lots of different locations there, and between different locations we've got a distance associated with them. So we're getting this view of what's going on, and he introduces one of our characters, Dr. Cerulean, who unfortunately has moved off this plane, and describes his history. So please do, it's a very entertaining series, so do spend some time reading there, because there's this wonderful story that's building with it as well. So I'm not going to go through the story, I'm not going to steal the thunder. I would recommend you go away and start reading those. But what we're going to do is we look through this, and we're introduced to a character, Moongirl. So she's got a band, so Moongirl and the Bullhorns are her band, and she's looking to get to a venue And I talk about how the traffic in Saxonburg is not great. So we're talking about how is she going to get from the beach where she's been spending some time, and she's headlining in an act in this Grand Theatre de Rabat. So how is she going to get from the beach to there? And she also wants to stop off along the route, or wants to look if there's an opportunity for her to be able to stop off along the route to visit the statue of Dr. Oh, I've got to make sure I pronounce his name correctly. Dr. Cerulean. Dr. Cerulean. So, let's dive in. So, he talks about data ingestion. So what we're going to do, I'm now going to switch over to the Sandbox. So Alex has posted a link into the Sandbox, so let's do that together. So I've gone to neo4j.com/sandbox, and what I'm going to do is click on the Launch Free Sandbox. So what Sandbox is, as I mentioned before, it's a really easy way of being able to try out Neo4j. You don't have to download anything, you don't have to install anything, you don't have to manage anything. Think of it as a cloud-based service that you can use to be able to try out Neo4j, try some queries. And the really good thing about Sandbox as well is that you have a number of use cases you can work with. So you've got blank Sandbox. So if you know exactly what you want to do, maybe you want to play with connecting with some of our drivers, or you've got some data that you want to work with, you know specifically what you want to do, you can do that. But we've also got a number of use cases. So if you want to have a play around with Neo4j and you're not entirely sure what you want to have a go with, you've got a number of great use cases that you can work with, and the data's already loaded there, and you can get going really, really quickly. So you've got a number of ways of how you can log in. So if you're signing up, you can either use your favoured social media single sign-on option, or what you can do as well is you can just put in a username and password and get signed up like that. So I'm going to use Google Login for this. So I'm just going to quickly get logged in. So there you go, nice and easy, I'm set up. And what happens if you're completely new to Sandbox, then what you can do is, if you're new to Sandbox, when you log in, what happens is you'll get this notice, and this will talk you through the various elements of the Sandbox. So here, it talks about projects and various settings that you have and so forth. So I'm just going to come out of this because, what's going on here? I'm going to come out of this because I know how to use Sandbox. So I'm going to give you my spin of the tour. So what you can do, so when you sign in for the first time, you'll see it says here Twitter and action required. You can ignore that. So one of the examples that we have, the use cases, is the Twitter use case. And what you can do is you can import all of your Twitter data and who's followed you, who likes you, etc., and get like a view of the mappings and how that reaches. But you need to get that integrated and pull Twitter data in. So don't worry about that. I don't have my stuff in there, but it pops up, so you can safely ignore that. So to get started, what you can do, you click on New Project, and then what you'll see is you've got a number of these projects, these use cases that are shown that you can have a play with, work with. So again, anything from network and IT management to the Women's World Cup 2019. You've got recommendations engines using movie data. You have got the very famous Panama and Paradise papers if you want to explore that data set, and so forth. So you've got a number of options there you can look at and play. And if you go, no, what I want to do is I just want to work with blank Sandbox, you can do that too. So what I'm going to be doing this week, because I'm going to be using one of the graph algorithm sections, graph algorithm algorithms, whilst your session. So I'm going to use the graph data science example. So this does have the Game of Thrones data set in there. I'm not using that, so what I'm going to do is I'm going to select this and I'm going to get rid of that data so that we can load the data from this blog post. So that's what I'm doing here, but just to show you have a number of examples here you can work with. If you're not sure about what you want to do with blank Sandbox, you have options there. Just a couple of things to mention about this. So I'm going to launch this so this can get set up. You have a couple of options here, so something to bear in mind is The sandbox initially lasts for about 3 days and then it will expire. So you do have an option to extend the sandbox. So if you're working on something and you need a little bit more time to work with it, then you can extend it. And I'm going to show you, once this is loaded up, I'll show you how to do that. You're not limited to the number of sandboxes, so what you can do is, if 1 week you want to work with the Game of Thrones data set using the Graph Data Science library, you can, and another week you want to have a look at the network example, you can, so you can spin up more than one of these. So that's now set up, so let me just quickly show you a bit of information about this. So you'll see this little down arrow next to the sandbox, so click on that and then you'll see you've got a number of options here. So if you want to extend your sandbox, so you can click this and this will add another 7 days. So bear in mind that the maximum amount of time you can have for a single sandbox is 10 days. So do bear that in mind. So don't, just in case you start bringing over huge amounts of data and do some intricate processing, make sure you've got some kind of a plan for how you can recreate that, say on a local instance of Neo4j. And other things as well you can do, you can get the connection details. So this is really good if you're using some of the Neo4j browsers, or maybe you've built an application and you want to get it to talk to a Neo4j database, and let's say you've built out some, an example in the sandbox, then you've got the information here to be able to connect it up. And so you've got the information there. So you've got the browser address. So this is effectively we're going to launch in a second. You've got the Bolt URI and so forth, and the various ports that you need to get started. And last but not least, you have an option here, connect via drivers. And what you'll find here is you've got some sample code that shows you how to connect. And what you'll see, so let's look at JavaScript, for example. What you'll see is that the information, such as the address for the driver and the authorization, authorization information, so your username and your password. So the password's generated each time you create a sandbox. That's already been pre-populated for you. So I could copy this code sample and immediately connect to that sandbox. And so here what we've got, so this example here, what this query is going to do, it's going to match everything in the database and it's going to return the unique identifiers for the nodes. At the moment, so this is not blank sandbox, we've got some data in there, so this would bring back all of the internal identifiers for all of the Game of Thrones nodes that are in there. So that's quick tour of the sandbox. Let's get going. So I'm going to click here, open with browser, and this is going to sign me in to the sandbox and start up the browser. And again, for those of you who have not used Sandbox before or not used Neo4j before, you'll also get a little tour as well that shows you the various places to click. So I'm not going to go through that now. If this is something you've not come across and you'd like me to do a run through, do ping it in the chat, and if we've got some time at the end, I will go through specifically the various bits of browser. But you do have that available to you, so if you spin up the Sandbox, you'll get this nice step-through guide of the various elements of browser. Okay, so you can see here when you start up a sandbox, you'll get one of these things called a guide, and the guide will talk you through the data that you're doing. So you can see here I can click through and it gives you the information of what this sandbox is. So I'm only using this sandbox because it's got the Graph Data Science plugin, because that's what I want to use. So I'm not interested in this data. So if I click here, you can see I've got sort of 2,600 nodes and nearly 17,000 relationships and various types and labels being used. I don't want any of that. So the first thing I'm going to do is delete all of that. So I'm just going to do this. There we go. So getting rid of all of that. So now I've got an empty database, and you still see these tags, and it could well be that we have some indexes on there, which is why it's showing that. But we can safely ignore that because we now have removed all of the data in our Sandbox database. Okay, on we go. So the first instruction we are given is to load some data. So we're going to click on this link, and I'm going to get a copy of all of this here, and I'll quickly talk you through what's going on here. So what we're doing here is let's make it a little bit bigger. Top tip, if you're using browser and you want to make the query window bigger, press the escape key. To make it small again, press the escape key again. So we can see here what we're doing is we are creating, or we're merging many nodes. So a node with label metro. So if we just quick recap of what a property graph database looks like. So we have nodes and we have relationships. Nodes have labels. So label indicates, what category that node is. So here we've got metro, so we're going to say these nodes are of category metro, and relationships have types, and the type describes what kind of relationship it is. And obviously a relationship only exists when it's connecting two nodes, so that relationship describes how those two nodes are connected. So for example here, we have a relationship of has root, so basically we're saying how there's a route between these two metro stations. And with both the nodes and the relationships, we can have properties, and the properties further enrich and describe what that node's about. So in this example here, we've got a property of name. So that's basically saying that our metro nodes have got a name property, and this is going to describe the stops. So if you remember that map, and let's go quickly back up to the map, you can see each of these places have got a metro stop, and you'll see these numbers here. So these are the properties that we're going to be putting on the relationships, and that's describing how far apart the various elements are. So I'm just quickly scroll back to here. So this is what we're doing. So what merge does, merges, you've got two ways of how you can create a node or a relationship in Neo4j. You can use the create statement, and what the create statement does is it just goes away and creates. What the merge statement does, and this is another way of how you can create nodes, is it says, I'm going to check first whether this pattern exists. So when I say pattern, a pattern could be a node on its own, a pattern could be a node and relationships. So it varies. So I'm not going to go too much into that. But what merge does, it goes, does this pattern exist? If this pattern exists already, then I'm going to sort of treat it like a match. So match is is equivalent of select in SQL. So match, it basically says match this pattern and then put it in our little variable, our container, to hold that information. So merge will do that if it exists, and if it doesn't exist, then it'll go off and create it. So it's a good way of saying, well, I'm going to do something with this pattern or this node or this relationship, but I want you to create it if it doesn't exist, but if it does exist, then just match it. So that's what's going on here. So you can see here we've got a lot of metro stations that we are merging with their names. And then the next step, so you can see all of these names here, these are like our variables, our placeholders, where where the match of the create executes and puts a reference to that pattern, or that example here, the patterns of nodes. And then we are now merging the relationships. So again, if those two nodes aren't already connected with a has root and a travel time of 2.5 in this example, then create it between the nodes, otherwise just bring it back as a match. Or actually won't bring it back as a match because we've got no reference to it. But that's what's going on. So here we are creating a bunch of metro stops, and then here we are saying how they're all connected. So let's go away and get that executed. And then what happens next is we bring that back and have a look at what's going on. So let's do match n, return star. So what this basically says is, when we say match n, we're saying, because we've not put in a label, we've not put in a node and then a relationship to another node or any patterns, we're basically saying match everything in the database, and then return star, return everything. So let's do that. And make this a little bit bigger, and then what you will see, as is mentioned in Jasper's blog post, is this doesn't quite look like the map, but that's okay. And let's talk about some of the reasons why this isn't going to look exactly the same as the map. So obviously, how nodes are being brought back, it's going to be at random. So obviously we've got no positioning here, and there's some funky things that we could do to fix that. But the other thing going on here as well is this is just generating. It's not going to look at, it doesn't know, for example, what to do with the properties on the relationship type. So it doesn't know that that's an indication of length. So if we had some clever layer on top, and in fact, one thing that's just jumped up in my head that maybe in the future we could ever play with, I mean, we're not going to do it today, but one very active person in our community, Estelle, she has put together this Neo4j graph app called Neo Maps, And what you can do there is you can specify lat long positions, and then you can create a graph, so you can start visualizing. If you've got any sort of geographical information in your notes, you can go off and visualize that. So we'd probably have to do a bit of crafting with this data to try and generate some points, or maybe we can use the image which is in the blog post and try and generate what would be the locations for that. But you know, you'd have to do some work to sculpt this. But anyway, what is here? But if we quickly inspect what's going on, you can see here we've got all of our metro stops. And what happens when you view a graph in browser is it tries to be a bit clever. And if you've got, for example, a property called name, it's going to assume that that's something you probably want to see, which is why it sort of automatically added the names here. Then you can see the relationship type, so you can only ever have one relationship type. And you can see as I hover over the relationship type, and at the bottom, it shows us the property. Okay, so we've got our data loaded in there, and let's see what we do next. So Jasper goes on to talk about graph theory and how it came from the Königsberg Bridge problem. So again, if you've not come across it, if you Google the 7 bridges of Königsberg, you will find a lot of material about that. So do go and have a look at that. And he talks a bit about the different kinds of areas you might use graphs, why they're useful. So I'm going to leave that. You do have examples as well if you want to explore the recommendations engine or fraud detection. We have those examples in the Sandbox, so do go away and have a play with those. And talks about bi-directional relationship. So let's talk a little bit about this because it is relevant here. So if you have a look, you'll notice that all of our has-root relationships have got a direction on that. And the reason why that is that when you load data in Neo4j, you have to provide a relationship direction when you're loading that data. However, the relationship direction only matters if you want it to matter. So for the purposes of route planning, a relationship direction might matter if you've got, I think you've got certain examples in transport systems where you can only go around in a certain direction, and you don't have like tracks in both directions, so you have to go around in a big loop. So something like that, if we were doing route planning, we would care about the relationship direction. In this example here, where we're assuming you've got double tracks, so trains going both ways, the relationship direction does not matter. And we can do that with Neo4j. So when we're actually querying, so when we're using our match statement, if we don't have to specify the relationship direction, and like that we can ignore the relationship direction. And I'm going to show you when we do shortest path, so like this is in Jasper's second article, I'm going to show you how we can tell the algorithm to ignore the direction of the relationships. Okay, so continuing on, we talk about here, and we're going to start exploring some routes. So let's bring back this query. So I'll quickly talk you through what's going on here. Just make this smaller. Oh. Right, and basically what's going on in this query here, we're saying match metro has route metro. So notice we've gotten rid of the direction. So straight away saying we're not worried about the instruction. Now, something interesting going on in this query, and I'll explain to you what's going on and little tips and tricks we can do. But what's happening in the query saying is match metro has route metro. So basically we want to match all of the neighbouring metro stations. So for example, if we look here, Brooklyn to Uptown. And then what we want to do is we want to return the name of the source metro station, the travel time, so that's the property of the relationship, and the name of the metro station it's connecting to, and we're limiting the first 5 results. So if I run this, we get these. So just a quick thing to mention what's going on in this query. Because we've not mentioned a direction, and this is completely fine, what's going to happen is at some point we're going to have, let's take Cavite Island and Fort Tilden. So we'll have a Cavite Island and Fort Tilden, and at some point, if we returned everything, then we'll have a Fort Tilden Cavite Island with the same travel time of 3. Because what's happening is we're returning all of those pairs in a database, and it's going to flip them as well, and that's fine. So we've got a couple of tricks that we can use to tackle this. So we can either go, well, actually, we'll put in the relationship direction because all we care about are the pairs. And just by virtue of putting the relationship in, we're not going to go 2 ways down the relationship. So this is one approach. Or another approach that we can use, so this is a slightly more efficient approach, but this is efficient because we understand and know the data model and we know specifically what question we're looking to answer. But another thing we can do, oh, excuse me, and this is a bit of a trick, is we can use internal IDs, and this is quite handy as well if you're trying to do some deduplication work, or you're just trying to stop this where you go down two ways without the relationship. And how you can do this is we can do a where clause, and I'm going to use the internal ID of the node. So what I can do is where ID n is greater than, and it can be less than, it doesn't matter. What we're trying to do here is just to force the conversation one way. So ID n is less than ID m. Oops. And again, same trick, that's the same idea. It's going to do that, and it's going to stop the two nodes from switching places as we go up and down the relationship twice because we don't have that direction. So I've gone slightly off tangent, but just explaining what's going on there. Okay, right, let's see. So we've got our list of metro stations and how far apart they are from each other. Okay, the image is not working, we'll check why in a bit. So you can see there's various routes and the average time has been recorded. Okay, so the next thing we are looking at is the most expedient route. So, can we find the quickest route between Cavite Island and to New York City? So if you remember, the band was down at the beach and they've got a gig in New York City in the evening. So let's start to see what's going on with the path. So again, I will talk you through this query and tell you what's going on. So in a previous query, if you remember, what we had was the node, and then we had just a single hop because we had has route, and then to so n has route to m metro. So that's just taking one hop. So that's only going to look at nodes that are directly connected to each other. But the other thing we mentioned, we didn't actually specify anything about the node. We specified a pattern. And patterns are super powerful if you don't particularly know what your start point or your end point is, but you know there's a particular thing going on. Well, what we can do as well, of course, we can anchor our nodes and say, well, actually, we're interested in a specific thing. And this example here, we want to have a look at the routes that get us between Cavite Island and New York City, or NYC. And so what we can do is we can specify the property, and this is us inlining the property. And then this clever little bit here, this is saying, I want you to go down this relationship type of has route, but I want you to go up to 6 hops out. So what this means is it's not going to just go to a neighbouring node, it'll go up to 6 traversals out. So we'll go up to a node that's 6 hops away from itself. And this is how we can start to span across the whole graph. So that's very powerful. But be careful with this approach, and I'll talk about that in a second. So what we're saying here, we're going 1 to 6 hops between these two metro stations. And then, so notice here we've got this path. So if you do this path, and this can be anything, Jasper's just called this path, but you could name this anything. But this sort of convention of your sort of variable name equals, that's going to capture the path. So this will capture your start node, all of the nodes that you traverse up to 6 hops away, and then your end node, and that gives you a set of paths. So this will give you a set of different ways that that both Cavite Island and NYC are connected. So we're taking those paths, relationship paths as well. So what this is going to do is this is going to extract all of the relationships out of the paths. And I suspect this is being done because we want to pull the property out of relationship. So I've got relationship paths as well. So this comes back as a map. So unwind rel. So if you've got a map, you can unwind it to bring back the individual items with unwind. So that's what's going on here. And then what we've got sort of a list function here. So with metro and nodes paths, again, what nodes will do is it'll pull all the nodes out of paths. So remember, we've got all of those paths from the route. And then a metro name is metro. So what we're going to do is we are going to be collecting, so looking at here, we've been collecting all the metro names as metro. We're going to collect all of the relationship travel times as streets. and then we're summing up all of those travel times. So what we're effectively doing is we're extracting out all of the names of the metro stations in that path. We're then extracting out all of the travel times that was the relationship property between the two metro points. So you think about all of the relationship points in that path. We're summing those together. We're now ordering by travel time. So same as in SQL when you use order by or group by or what have you. So you tend to order by ascending order. So you have to explicitly tell if you're descending. So because it's ascending, it's going to go from smallest to largest. So this is going to give us the quickest routes. So let's run this. And there you go. You can see we've got the travel time of 26. So this is going to list us all of the paths between those two stops up to 6 hops away. And you've got an example here. So here's our start point, and we've got 1, 2, 3, 4, 5, and 6. Our 6 hops from our start point, Cavite Island. So you can see what's going on there. And you've got actually a few of these. Actually, we've got a few with 6 hops out. So those 3 there, 6 hops out, and obviously they're quite long, 27, 51 minutes. So you can start to get a flavour of this. And do we have an example where, just for a bit of fun? Oh no, they're all the same. I was wondering if we've got an example where doing more stops results in a shorter travel time, but not in this example. 7. Oh no, so look, there we go. So 7 stops. This one here with the 7 stops is quicker than this one here with the 5 stops. So this is fun, and this is where it becomes really useful when you think about route finding. And route finding is not just going to be about, well, it's the shortest number of stops. You know, maybe there's something going on where, certainly if you think about driving, why do we take motorways? Motorways typically tend to be longer in mileage compared to, say, going through a country village. But with a motorway, you probably have a lower weighting because you can drive significantly faster. You're not going to be stopped by traffic lights and so forth in comparison to going down the shorter routes. Do I have an express? Could you, Akimark, could you just describe a little bit by what do you mean by express route data? And then we can come back to that. So you get a flavour of what's going on here. So I mentioned a note of caution about using the hops. A couple of things to bear in mind with this. So one thing that I would say is ideally I would suggest if you've got a smallish data set, not too many connected nodes, then this is okay. Generally I would say I would want to use this with a relationship direction, because just to bear in mind that if this is undirected and you've got lots of relationships, then there could be thousands if not millions of different paths that can join 2 nodes, and that can take a long time, if not, it may not even complete at all, because you may have millions upon millions of different routes that connect 2 nodes. So that's something to be mindful of when you're using this. Another thing as well is, and we're going to be using shortest path, is generally you probably want to wrap this inside another function which is going to discard longer paths. So for example, if we were doing shortest path, then what shortest path would do, shortest path would basically say, well, I've got path A is, I'm going to pick some arbitrary values, path A is 8, and then find path B is 6, path C, well I'm starting to go down path C and it's already got to 7, so I'm just not even going to bother going down path C because path C is not going to be shorter than path B. So effectively it's discounting paths. So whilst you may have, say, sort of thousands of different paths, what it's doing is basically getting rid of any paths that are obviously going to be longer than what it's already found. So that's okay, it's not going to go on forever. And just so you got a flavour of what's going on. So we've got a question here. During peak times, morning and evening, subways will designate some of their routes as express, which mean they don't have to stop at intermediate stations. Right, yeah, great question. So this, the articles which Jasper has done doesn't mention express routes. However, he does talk about closed stations, and I think you can take analogies from that and you can start to think about how conceptually you could apply that. So that's coming up shortly. So hopefully that's going to give you some ideas of how you tackle the express route option as well. Okay, so we've got our list of different routes. So we'll continue with the article. And yep, so we've made this discovery. As you can visit Dr. Cyrillian's statue as well, which is Intramus. So if we have a look, there we go. Yep. So I think that's all of the stop. Well, yeah. I think every single stop she gets to visit the statue. So that's good. So now, so this is coming back. Aki Mark, this is perhaps coming to your comment. So the example that Jasper provides here is how do you handle closures or road closures or route closures? So how to tackle route closures. So what happens if something closes? And again, coming back to your question about doing the express routes, this is something perhaps you can fit in. So maybe if a route's got a flag of express and maybe some other value. So you'll have to think about the data model. But again, as you mentioned, yes, this is a great use case for graphs. You can probably model accordingly. And here we've got here this example that Jasper talks about is, well, what do you do if something's closed? So what we're going to do is we're going to set an extra property in all of our nodes, which is the idea of status. So I'm going to set them to active, and then I think he's going to, he picks a couple that he's going to set to closed. So let's talk through the query. So here what we're doing, it's the same idea, we're going to match all of the metro stations. So this is metro station has route metro station, and we're setting the status to active. And you don't have to declare properties ahead of time when you're loading data. The really nice thing about Neo4j is if you discover there's a new property you want to add, just add it. You don't have to reload all your data. You don't have to have properties on all your nodes. You can only set it on the ones that are valid. You can get rid of properties as well. So very, very flexible. You can keep flexing and updating your data accordingly. Okay, so let's do this. It's going to set all those properties. And again, same idea. I think we've got 32, 23. Yeah, so what we could have done, if we put in the direction, then we've only done 32 updates because there's 32 relationships, but that's fine. Tiny data set, this is fast. Okay, so we're now going to make 2 stops closed. So again, I will talk you through what's going on here. So similar as before, we are going to pin our points here. So we've got 2 routes, so one route between Chinatown and Amita, and Intramus and Chinatown. Both those routes are closed. So what we're doing, we're finding our start point and our end point to locate the relationship between the 2 of them. And then we're going to set the status closed. So let's do that. Wonderful. So I suspect we're now going to rerun our query again. So let's talk you through what's going on here. So we're adjusting the query ever so slightly, and what we're saying here is, so we're doing the paths with paths as rels. So we're doing a where clause. So what we're trying to do is check to see whether or not the relationship status has active. So remember, all 30 out of 32 routes that we have between our metro stations are active, but 2 of them are closed. So what we're saying here is basically what we want to do is only have the paths where there's an active between the route between 2 metro stations. So we don't want the closed ones. And then everything else is the same as before. Don't worry doing it. That if the query scares you slightly, don't worry. When we move over to the graph data science algorithm, when we start using the shortest path with that, it's a lot simpler. So bear with me, we are making progress. So you can see what's going on here. And if I run this, then you can see we've changed things slightly. So whereas before it was 26 minutes, you can see the route's slightly longer, but we're avoiding the closed route. So you can see the route between Intramus and Chinatown was closed, so we're now going via St Germain to get us around there, and so forth. So there we go. So we found our new shortest path, taking into account those closed routes. So again, if you're thinking about how would you handle an express route, so you can take some of the ideas here and refit your model to go accordingly. Okay, so we've done that. So that was the first blog post. So do go away and have a look at the blog post. And again, at the end of the session, I will repost all of the posts so you can have a read and work at them at your own pace. So let's move on to the second blog post. So this is where Jasper continues the story of what's going on. Again, I am going to let you read that at your leisure and enjoy the story. But let's have a look at the setup. So what you can do if you want to check what procedures you've got installed in Neo4j. So just let me wind that back a bit. What you can do with Neo4j is you can add stored procedures to the database. So for example, if you want to create some custom function that works with your database, let's say you want to build some extra functionality, let's say you want to work with our traversal APIs and so forth, you've got a lot of tools where you can really, if you really want to get that sort of high performance, or there's something really specific that you want to get working that you can't do through Cypher alone, what you can do is create a stored procedure. And what we have is we've got a plugins folder. So if you go to the plugins folder where your Neo4j instance is, you can pop that jar in there. So your Java-based or JVM-based plugin there, you can drop it in, and then you can call it from the database to work your extra functionality. Now we've got a number of plugins, so sort of official Neo4j ones, which kind of work on this concept. So some of you may have come across APOC, which is a package of components, which are a lot of helper tools for Neo4j. So some of you may have come use them for importing data or using JDBC connection, or maybe you've time to live or triggers and so forth. So you've got 400 plus helper functions there. The other plugin that we have as well, and there will be more, so I'm probably missing a few, but the other one we have as well is the Graph Data Science library, which again uses this same idea where you drop the Graph Data Science library into your plugins folder, and then you can use them. So in Sandbox, you can't add plugins in Sandbox, but the reason why I've used the Graph Data Science one there is because it's got the Graph Data Science plugin. So if I call this dbms.procedures, this is going to let me know what I've got available to me. And as you can see here, everything here that says APOC, so we know that we've got APOC available as a plugin on our database. But if I scroll down, we should see something that says GDS on there as well. There we go. So we've got GDS as well. So we can see that we've also got the GDS plugin available to us as well. So that's one way to check to see what's available. Second blog post. So doing this, and we're going to be doing another sort of, so again, reminder of the map. Oh, okay. You remember what the map looks like, my internet probably being a bit funny. And then what Jasper starts to talk about here is, he starts to talk about that we've got effectively what we've got is a weighted graph. So you've got two ways of how, when you're thinking about shortest path, there's two ways you can tackle it. So one route will be, well, I've got my graph, and sort of let me bring back as a reminder. Actually, let me just scroll down. It's probably quicker if I just scroll down. So just as a reminder, we've got this graph here, and you know how all the things look of equal length. So if we ignored that each of these has a weight on them, if we did shortest path, in fact, what we can do, let's modify one of these queries quickly so that you get an idea. So if I want to do shortest path and I wasn't interested in the travel time, so what I could do is I want to do, just going to change this to size, I think it's now, isn't it? Size. Because what I want to do is I want to sum the number of nodes that we've got. So metro, I think we'll do it. No, metros. And let me order by metros rather than. Okay, so this should hopefully. Oh. Alright, let's see if this works. If not, I'll talk through what's going on. Okay, let's leave it for now. But I'll need to rewrite this query. But basically, if we did it just by size of path, so remember we were going between Cabot Island and New York City, so I think here it happens to be that the shortest route is the shortest number of nodes, but you kind of get the idea that just because 2-3 nodes are close to each other, or you only need to go via 1 or 2 nodes intermediary to get to your route, doesn't necessarily mean it's the fastest, because we've got that weight on there. So if we go back here, so we're talking about weighted, we've got weights on here, and what we can do is we can do a weighted shortest path to be able to let us know, what's the shortest path based on the weights that we've provided. So it talks about Dijkstra's algorithm, and let's get started. So again, this is the same idea. So this gives you the instructions about how to load things up. So what we're going to do is we're going to be doing what is called an anonymous projection of the graph. So for those of you who've not come across the GDS library before, don't worry. For those of you who have come slightly, what we're doing is an anonymous projection. So when you're using the Graph Data Science library, you need to let the library know what your graph looks like that you're going to run an algorithm on. And the thing to bear in mind is that it's not always a given that the data that you've got in your database is shaped exactly the same as the data you'd want to run a graph algorithm on. So let me give you an example. So let's say I had a database, and in this database I was collecting the different ways that a group of friends communicate to each other. So maybe I do something like a person emails a person, or a person phones a person, or a person WhatsApps a person, and so forth. So we've got like lots of different nodes going involved. But if I wanted to do something like who is the most influential person in this network, and that's probably going to be based on something along the lines of how different people are contacting them. We don't care about the different means of communication. So what we'd do is we'd need to project a graph that said, well, actually we've got person connects to another person. So we're dropping those intermediary nodes. So that's what projection is. And you've got 3 ways of how you can do projections with the Graph Data Science library. So again, this is all about letting the algorithm know what the shape of the data is that they're going to be running against. So you can either do a native projection. So this is where we're in that happy place where actually all of my data in the database is exactly the right shape to run the algorithm. You can do a cipher for projection, where you use cipher, the Neo4j query language, to let the graph algorithm know what the shape of the data is. Or what you can do is a anonymous projection. So anonymous projection is using either a native projection, i.e. data is in the right shape, or the cipher projection, i.e. I'm letting it know. But the big difference here is with the first 2 that I mentioned, we are loading that graph into memory and we keep it in memory. So if we need to rerun the algorithm with a different parameter, or we want to run another algorithm that uses the same shape of data, we can. An anonymous projection basically means we run that, we load that memory graph into memory once, we run the algorithm, and then we just drop it all. So that's what's going on here, but it's all good. So don't worry too much about that if you're quite new. There's a lot of information in the docs. Again, if it's something of interest, ping a question in the chat and I can point you to the right resources. But I digress. Let's come back to here. So here in this example, we want to find out the shortest path between the metro stop Pigalle and the ruins. And what we're doing here is we're using call. So if you're calling a procedure, so you've got 2 types of things you've got in these plugins. You've either got a procedure or a function. So we call procedures, and then functions we just sort of use as part of the query. So here we're calling our procedure, which is shortest path. And this stream means we've got a couple of, we've got a number of ways we can use the output of our graph algorithm. So we can either make writes, we can make modifications to our database, we can make modifications to our graph projection that's in memory, or what we can do is we can say, well, we don't want to make any changes. What we want to do is just stream the information out. So if you think about if you're generating routes or doing route planning, you just want to stream the information out. You don't want to make any changes to your graph. So this is what the stream does here. And then what we're saying here is node projection metro. So it's letting it know, well, the node label you need to use is projection. And then we're saying the relationship projection. So we're now giving information about the relationship joining our metro nodes. And here we're saying, well, we're using the relationship type has root. So you've got type here has root. The property that we're interested for the purposes of weight is travel time. And here we go. So you know how I spoke about earlier that whilst you must provide a relationship direction when you're writing data to your database, but when you're doing queries against it, it doesn't matter. And this is how we tell the graph algorithm that it doesn't matter what the orientation is. So here we're saying undirected. Doesn't matter. Ignore the direction. And then here, what we're saying is we've got start node A and node B. So this is effectively the way we describe. This is basically how we're describing. And start point and the end point. And then here, what we're doing is we're yielding the node ID and cost. So what we're doing is we're yielding the nodes on that path, and we're also, so basically bring back the nodes. So these are the internal IDs that will come back, and the cost is basically, what is the cost to get across all of these nodes. So not that dissimilar to what we saw previously. And then what we're doing is, so now we're using a function from GDS because we're not using the call there, as you can tell. So we're just using this helpful little tool that's going to take the internal ID that's returned and turn it back into a node so that we can do stuff with it. And here we are going to be returning the nodes, the cost to get between them, and the journey time. And the cost is journey time. We're basically saying, call it journey time. So let's run this. And there you go. So what you can see here, this is the shortest path to get us between the ruins and Pigel. And if I go to the table, we should be able to see the other values as well. So you can see between each stop, this is the cost to get. So as we keep accumulating each of the nodes, this is the cost between them. And we can prettify that a bit as well. So I think if we do, if I do return collect, was it name, wasn't it? Looking at label, yeah, names, and let's do some cost journey time. That we should get the collection of the names. There you go. So you've got the collection of the names. So these are all of the stops, and you know what I've done here? Ignore the journey time, because what's happening is it's collecting all the summations. So if I go here to the bottom, then you can see, here you go. So that's the total journey time is 29.5 seconds. Now, to bear in mind that we have the closed section as well. So again, Jasper looks at how we handled those closures again. So we've already got the active and closed. So we're going to update those. So actually, let's just rerun this and update those quickly. And this one, and then we're going to do the same thing. And what we're going to do now, so the first time around when we used the this anonymous projection, we used the we used the native, so i.e. everything's in perfect state, just pull it straight up from the graph. But this time around, because we now have to deal with those closed routes, we're going to use the cipher version of the load. So I'll talk you through what's going on, and then it'll all make sense. So here, what we're doing, so again, same idea, match A, match B. So those are our start point and the end point, A and B. And then what we're going to do here is we're saying, well, actually, I'm going to tell you the nodes. Again, we're doing this match metro return ID and as ID. So we always give the internal ID. So we're matching everything that's a metro node. So in this database is literally everything. So you can't mix and match native labels with cipher relationships and vice versa. So either it has to be all native, you give the node labels and relationship label, or it's all cipher, you have to do that. So here we're saying every metro node is what we want to use. So return ID as enter ID and returns the internal ID. And then our relationship query, and this is what we're saying here, is saying match metro has root metro, So this is bringing back all those pairs where our status is not equal to closed, and then we're returning the node ID of the source. So n is our source and the node ID of target. So graph data science always wants node IDs. So when you're telling it what's connected to what, you're always giving it the source ID, the source, which is going to be one node, and the target, the other node. So it doesn't worry about the relationship in the middle. So that's the identifier. And this is a really good way of dropping that information in the middle. So if you think about the example I gave about, finding out how different people are connected to each other via communication. So this is an example of where we're ignoring the WhatsApp message or the email or the phone call, and we're saying, no, we just give you the source, the source node is person A and the target node is person B. Here's internal IDs, and assume that they're directly connected. Aha, so one question that's come in, why have I used not equals to closed instead of, or bracket closed instead of active? It doesn't matter, they're both the same. I guess being pedantic about it, if there was any other status like semi-open or express or whatever, then all of those would have been included. So it's only going to exclude anything that has a closed property on there. Whereas conversely, if we had equals active, then it's only going to include those paths where there is our status equals active. But in this example, it completely doesn't matter, and you could have done either. Both will do exactly the same thing. Okay, so going back to example, we're saying what our start node is, what our end node is. Here's our travel time is the weighted property, so all same as before. So let's return. And here we go, so same idea. If we scroll down, we can see we've added an extra, I think that's about an extra 5.5 minutes to our journey time when we take account of closing. So we've got a question that's come in. What do I mean by native? I thought everything was in Cypher. Yes, sorry, slightly confusing language, I do apologise. So absolutely, Cypher is our native query language. But when we come to the Graph Data Science library, you've got two mechanisms of how you create this graph projection. So you always have to get your data of the graph you want to run your algorithm of into memory. And the reason why we do that is you might need to do some shaping to that graph. So for example here, we had to shape the graph to only go down those active routes. And what we mean by native, it literally, when we say that, we mean straight from the disk. So when we talk about a native projection, we're not inventing. So Cypher absolutely is our native query language. But in this context, when we talk about the Graph Data Science library, what we're saying is we're lifting straight from disk into memory. We're not applying any queries or conditions to our nodes of the relationship. So if a node has got a certain property or a relationship has a certain whatever, none of that. We're literally saying, well, we go to the database and we just pull that data immediately into memory, and we don't do any pre-processing. So that's what we mean in that context. So hopefully that makes sense, and I've not confused you too much there. So no, absolutely, Cypher is our query language. It's just what we're talking about here is what we're doing to the data before we run a graph algorithm. Perfect. Okay, so we can see here, so what we've done is we've used the shortest path algorithm here from the Graph Data Science library. So we've effectively, over these two blog posts, Jasper's talked about two different approaches you can use to do the shortest path. And what you will see is as you've got more routes to go down, or you've got more paths, you're going to want to use the shortest path algorithm, just because it's going to be significantly more efficient at processing your shortest path whilst discarding paths that are too long as it goes along. So those are two great posts. So let me put links for those again. Do go away and have a look at them. They are very good. There's a nice amusing story with those, and I am really looking forward to the next instalment from Jasper. So check those out. Again, if you want to follow Jasper on Twitter, let me give you the link for that as well. And last but not least, just as a reminder, if you want to have a go at doing this, so you will want to have the one with the graph data science example as we did earlier. So do have a go on Sandbox, and Mark, I will have a look at that link, and maybe that'll be a future blog post by me to have a look at, and then I can talk about my own blog post on Twitch. Excellent, cool. So if there's no more questions, I will leave it there. So I'm going to stop the stream shortly. If you've got any questions, I'll be around for a few moments after, so I can pick those up. And otherwise, thank you very much for joining me. Don't forget, as well as myself, my colleagues Will Lyon and Adam Cowley and Michael Hunger are all doing streams as well across different parts of the week. So I would recommend you have a look at our schedule on Twitch. So if you go to twitch.tv/Neo4j_/about, you will see our schedule there. If you want to be notified when we go live, then I would recommend you follow us on Twitch. And also, if you have a look at the Neo4j account on Twitter, we tend to ping an hour's notice beforehand when we're about to go live. So thank you very much for joining me, and hope you have a fantastic day. Bye.